Hi y'all, welcome back. So previously we have derived the velocity profile for the velocity in the theta component. So we have arrived at u theta equal r over 2 times c1 plus c2 over r. Now, in order to get the exact solution or a particular solution, you would need the boundary conditions, okay? So let me write down, right? In order to solve for C1 and C2, we need to plug in the boundary condition. Okay, so what's the boundary conditions? Let us draw the circle. Okay, so we have y, x. So our velocity, if you recall, is measured in theta direction, right? So let's say at an angle theta here. Okay, so you have this is at x equal infinity, this is at r equal infinity, r equal infinity here, and this point right here is r equal big R constant. And at this point right here, if you remember from your physics class, we have the angular velocity, u tangential. Okay, so what's the boundary condition? Very simple. The first boundary condition say the velocity at r equal infinity is 0 because the fluid is at rest. It's like you see a spinning tornado, but you're looking from afar, you see a calm surface. So that's what it means. The second boundary condition is say u theta at r equal big R equal to omega times r. This is the angular velocity formula from physics 1. Okay, now after that you can definitely plug it in. So let us plug in the boundary condition. Okay, so what do you have? At u theta at r equal infinity equals 0. So what does it mean? It means that c1 times infinity over 2 plus c2 over infinity equals 0. Okay. The second thing say u theta at r equal big R constant equal omega times big R. What does it mean? It means that r over 2 times c1 plus c2 over r equal omega times r. Okay, let's solve for c1 and c2. So you know that c2 over infinity is 0 already, so all you have left is c1 times infinity over 2 equals 0. Okay, and this equation right here, I'm gonna keep rewrite it. R times c1 over 2 plus c2 over r equal omega times r. Okay, you notice something very interesting about this term right here on the left, the highlight term. c1 times infinity over 2 equals 0. So in order for that to be always true, c1 have to be 0. So that 0 times infinity over 2 is 0. Okay, so it can be inferred that, okay, let me switch color. You can say that c1 equals 0, and then you rewrite it r1 times c1 over 2 plus c2 over r equal omega times r. Okay, so now you can plug this in the previous equation, the below equation, to get c2. So c1 equals 0, r times 0 over 2 plus c2 over r equal omega times r. And after some simplification, you get c1 equals 0, and here you get c2 over r equal omega times r, because r times 0 over 2 is 0. Cancel out. So you get C2 equal omega times R square. Okay, wonderful. This is the C1 and C2 we're looking for. And if you plug in the original function, remember so what does the velocity profile looks like? What does it look like? You recall that u theta is a function of small r. R over 2 times C1 plus C2 over small r. We already derived this expression above. Now we just find C1 and C2 right here. Right? So you're gonna plug them in here. So you get equal R over 2 times 0 plus omega R square over R. So eventually you get u theta as a function of R equal to omega times big R square over small r. Okay? And ladies and gentlemen, this is our velocity profile. This is our velocity profile. Okay? That is it for part D. Now let's go ahead and move on to part E. Okay, what does part E say? Part E, let me write in this color. Part E, they ask for the momentum balance for the radial direction R. Okay, so what do you do? Again, the place of the equation, which equation do we use? I think it's the same page. Let me check. Yeah. So it is equation. I'm gonna write here. Using equation 5.75, page 282. Just want to make sure 282 is it true? Yeah, 282. Okay, let's write the whole thing down and we see what terms cancel out. Okay, so if you write the whole things out, you get rho times the partial of ur over ut. This is this the change of velocity over time, the partial over time. Plus ur times theta of ur over theta r plus u theta over r times theta of ur over theta of partial of theta minus u theta square over r plus uz times partial of ur over partial z on this. Okay, equal negative partial of p over partial of r plus mu times partial of r with respect to 1 over r times partial of r times ur over partial of r plus 1 over r squared times partial of partial square of ur over partial theta square minus 2 over r squared times partial of u theta over partial theta plus partial square ur over partial z square. Okay, plus rho g r. Okay, so what term can we cancel out? Now, let me zoom in a little bit for y'all. The first thing you'll notice that this is a steady state again, so we don't have the time, there's no change of ur over time, so partial ur over t is 0, so we say because it's a steady state. The next thing we can say, this is cancel out because we already determined ur is 0 in part A. This term right here also vanishes because ur equals 0. This term right here stay. This term right here vanish because uz equals 0. All this right here cancel out because ur equals 0. My bad. This term right cancel out because ur equals 0. This term cancel out because of the continuity equation. So because of u theta over theta equals 0 due to the continuity equation. Okay. The last term cancel out because ur equals 0, and this term cancel out because there's no gravity effect, which means that there's no gravity components in any direction, including the r direction. So gr is 0, then rho times gr is also 0. So what term do you have left? You have, okay, I hope y'all can see it. You have these two right here. Let me highlight this. You have this guy and this guy left. Okay, and two of them are equal. So what have left? You write. So what can be inferred is rho times negative u theta square over r equal partial pressure over r. So if you take away the negatives both sides, or you time both sides to -1, you get partial p over partial r equal to rho times u theta square over r. Okay. However, this problem like here, they want us to find a complete formula. Remember, we know what's u theta. Okay. We know what is u theta from previous problem. Okay, so what's u theta again? U theta, we only show this here, omega r square over small r. You can substitute it in here. So the partial pressure in the radial direction equal to rho times omega. I can substitute this omega r square over r on that square over r. Okay, because you just substitute this thing in from previously, and if you simplify it, you get rho times omega r square r4 over r square over r. So eventually you get partial pressure over partial r equal to rho times omega square times r big R4 over r small r cube. Okay, wonderful. So what needs to be done here? Okay, so you need to solve for the pressure, right? So this is how I'm gonna do it. I'm gonna write it like this. So this is rho omega square r4 r to -3. Okay, so I will times partial r both sides. So partial p equal rho times omega square big R4 and then r to -3 partial r. And if you integrate both sides, again, the goal is to find a pressure profile. Okay, we try to find a pressure profile. Okay, so if you integrate both sides, this one you get pressure as a function of r. This one equal to rho omega square r4 times r to the -2 over 2, -2 plus c1. Okay, and if you rewrite it, you get p pressure as function of radius equal to c1 minus omega rho times omega square r to the power 4 over 2 times r square. Okay, that is your pressure profile. Okay, and just like the previous problem, in the next part of the video, we will find what's C1, and we will see what is the pressure gradient. Is it positive or is it negative? Okay, thank you for your attention, and I'll see you in the next video.